All right, I'm Tim. I'll be talking about a cross-language probabilistic programming protocol for physics and beyond. So our goals here are basically to turn any stochastic simulator you might have into a probabilistic simulator. We want to keep like the main strengths of Enzyme, which is low overhead and a minimal change required to your simulator code. And we want to be independent of any probabilistic programming system. So you can basically reuse the infrastructure. You can basically reuse all the infrastructure for any probabilistic programming system you might want to use. So let's quickly get back into probabilistic modeling. So we have a stochastic model which encodes prior knowledge and empirical evidence about a problem we might want to model. And that is modeled as a joint probability distribution on a set of random variables. So we have observed variables, basically, where we know the values. And we have latent variables, which are unknown. To solve those problems, the goal of inference is to determine the distribution of program parameters that could have given rise to an observed program output. We can then use Bayes' theorem to determine the posterior of such models in combination with a set of observations, which is shown here. So there are many inference methods you might want to use. The overall goal here is to approximate the integral for the marginal likelihood we just saw on the slide before, numerically by evaluating the integrand for many different x via, for example, Monte Carlo methods. The key idea behind that is with variational inference that you approximate that marginal likelihood integral we just saw down there. With a simpler form that can be solved in terms of a closed form expression, forming a lower and an upper bound of that, which then remains a problem of bound optimization, which can be solved numerically quite easily. So the two main inference methods being used right now are Monte Carlo, which I already talked about, which provides asymptotically exact results in the limit of a finite number of samples. But it's very expensive to compute. And then there's also variational inference, which does not provide asymptotically correct results, but is a bit less computation heavy. So for probabilistic programming, we basically use programming languages to model our problem, which basically we want to draw random samples from some kind of distribution, and we want to have the ability to condition those values of the random variables. So here's the comparison. Your normal mathematical model would basically, your normal program has parameters. Then there's the actual code of the program, and it yields an output, and we call that execution. And for our probabilistic program, we also have parameters. We also have program code, but we generate observations. And now with inference, we want to go from observations to likely parameters of our model. So for that, in probabilistic programming right now, to abstract that away, we use execution traces. Execution traces are just one possible way throughout a program which can be taken. We've got a very simple silly program over here, which can only, because it's so simple, take one path. So we just draw samples from a normal distribution here, call this function, which kind of does a prediction and computes the error here. So in our trace, we would first record that we called model. Then we would record each sample we sampled. So that would entail the likelihood of that sample, the actual sampled value. And we do that for every variable, random variable. And we also record calls in our trace and do the same for those. And yeah, we'll also be able to record gradients soon. Yeah, so here's like a schematic overview of what we actually want to achieve. We want to have our probabilistic programming system up here, which is implemented in Python or Julia. So stuff like Turing or Gen or Pyro come to mind here. And we want to be able to communicate with like our own C++ simulator over like a C interface, and want to basically generate those traces we just talked about. And that we do by first calling these interface methods, which I'll go into detail soon, which just help creating this trace we just saw iteratively. And yeah, those are like the primitives we would use in our to generate those traces. OK, here's the first one. Enzyme sample. So when we want to update our simulator to be our stochastic simulator to be a probabilistic one, we basically need to wrap every call to a random number generator, or yeah, to like a sample call inside of enzyme sample. And what we want to tell enzyme here is which function we use for sampling. We want to tell enzyme how to compute the likelihood. And we want to give it an address so we can like uniquely identify this sample in our traces. And those are just the args for the sampled function and the logprop function. We also have, for trace generation, we have enzyme trace, which takes like our model function we want to trace. And we can also pass an interface dynamically to that, which that would just be implemented, for example, in Python or in Julia, and it would just basically map to whatever the native trace object for example, for Pyro or Gen is in that case. And we also have an intrinsic for conditioning, which again takes a function, takes arguments to that function, but this time we also take another trace, which can be drawn from like a previous sample. And in that trace are like values we want to condition. So we basically define the values we want to see there beforehand at a certain address. And again, it takes an interface, which we will just use for creating those traces. Yeah, here's how this trace interface would look like. It's basically an array of void pointers to all those functions, which you would have to pass to enzyme. Yeah, so now we go into the trace interface, so how enzyme would use that interface. And the first function of that interface is new trace, which basically instructs the probabilistic programming system to create a trace for us. So that would be then a native Pyro or Gen trace for the Julia case. And we also have interface function to free that trace at the end to clean up. Then again, we can, whenever we encounter like this enzyme sample function call in our simulator code, enzyme will then go ahead and during compilation will insert a call to enzyme insert choice, for example, for a sample, which will take the trace pointer, which is propagated by enzyme throughout our whole simulator, an address, which you passed to enzyme sample, and like a score, which will be just the evaluated likelihood function based on the sample we actually get. And the return value will be the sample, which can be like a void pointer, which can be the double or any more complex struct you might want. And yeah, the size of that struct we pass as well. And yeah, for calls, enzyme calls enzyme insert call. And yeah, we basically pass the trace again for which we want to record that call and the address of that, and the subtrace we'll use for the invocation of that function. So each function has its own trace object, which are then linked together. OK. Enzyme also has the possibility to like get choices and likelihoods. This is important for differentiation later on and also for conditioning. So whenever we do conditioning, enzyme can ask for traces for a certain address. This might be the address of like a function call. Then enzyme can also retrieve choices of this condition of the trace of observations we have. So basically what we pass to conditioning. And then we can also get the likelihood, which becomes relevant for differentiation later on. And yeah, to kind of check that there is actually a choice which we can draw from the conditioned trace, we have also functions to tell us that. So if we have a conditioning trace where, which does not contain a sample for our address x, we choose to do a proper sample instead of relying on the conditioning trace. Okay, here's like a whole example again, which again is just we're trying to fit like a curve here. And this is how you would use all those primitives. So we replace our call to which would have been normal with enzyme sample, passing the distribution, the likelihood, and the address again, and the parameters for the normal function in that case. And yeah, enzyme just then generates traces for us. So here's how we would invoke the tracing for the given example we saw. We just basically call enzyme trace, pass the function we just saw, data maybe, the size of the data given depending on your model, and the interface we already saw. Yeah, that's the same for conditioning. You just need to pass an extra trace with values you might want to condition. And last but not least, we are currently working on differentiation. So for that, you can basically call this just like enzyme autodiff. You can duplicate your data. This should be enzyme const, the n. And yeah, again, you can pass 2 traces this time. A second trace will contain the gradients for you this time. And yeah, the same also works for tracing, which then just returns 2 traces and does not take any traces. Yeah, but this is currently in heavy development, so we might eventually change the interface to just to not needing to duplicate the trace and to just have one trace, which has the gradients as well as like these samples. Yeah, that's it from my side.
Okay, thank you, team. Are there any questions?
Questions? Comments? There is one.
Sorry, this is a very naive question. Why exactly does enzyme need to be aware of what I want to do with the gradients? Why do I need specific enzyme calls for sampling? Like if I think about classical sampling schemes, let's say HMC, I just need to gradient of the cost function to do efficient sampling. Why do I need to wrap the random number generator in enzyme in the first place?
Yeah, that's
I guess I'm just missing something, but
that's just to create those traces which kind of abstract away the so probabilistic programming is just abstracted away in the trace generating part and the inference library part. And so you would just pass that trace which was generated to an inference library to do your inference in the end. So that's just a way of decoupling those. And that's why enzyme needs to be aware of where you draw samples and where you call functions.
Okay, one quick last question, please.
Yeah, so I was just kind of curious. So you have all this trace structure. Can you then use it to actually pick your inference library? So if you know you have some typical graph structure of your probabilistic model, you may want to split it up and do something like a particle filter, a sequential Monte Carlo on a piece of it, HMC on a piece of it. Is there like a way to like hook this into the whole like trace structure that you guys get?
So basically the idea would be to just take your favorite probabilistic programming system and then using this interface, let's go here. Using this interface, instruct Enzyme or the simulator to generate those traces for you, which you can then use in your favorite system to do your inference.
Okay.
If I may, give a partial answer to that. I think the question you're asking is also heavily dependent on the probabilistic program system. So let's say we think about something like AEMCMC, where they do pattern matching on the graph to then construct a sequence of samplers. Then that would be a higher level up than from what is done here. So for example, what's done here is just the interface. So you would need to still get Enzyme to talk to, for example, AEMCMC, just as a random example, for that to then apply its methods. It does not actually do method selection or create a stream of samplers like you would in theory do for an optimal inference problem.
Yeah. Thanks.
Okay, if there are further questions, let's use a roundtable opportunity for those. Let's thank team again for presenting this.